Short number 5, Classical versus Quantum. As discussed in the short number 4, due to gravitational interaction with itself, white dwarfs and neutron stars collapse and transform themselves in black holes. Could this happen to quantum particles? How do we know if a particle is classical or quantum? Well, there is no wave associated with a classical particle, but there are two waves associated with each relativistic quantum particle. Is it a massive Fermi gas star a quantum particle? Are we quantum particles? Did anybody have ever observed the Schrödinger cat, the cat that it is a quantum particle, the one that could be simultaneously deaf and alive? Why has nobody ever observed the Schrödinger cat? In what follows, it is presented a possible answer to all these fundamental questions. Each classical particle has a mass and a size. Many quantum particles also have mass, but do they also have sizes? Well, looks like at least some quantum particles have sizes. For instance, as discussed in the short number 2, the Bohr radius characterizes the size of the hydrogen atom. The hydrogen atom is small but is not a point with null size. We know atoms and molecules are quantum particles because we can do double-slit interference experiments with atoms and molecules. Interference phenomena requires the existence of waves. What is the size of an electron? Some physicists prefer not to talk about the possible size of the electron. It is somehow easier to think that the electron, like all the fundamental quantum particles, is a mathematical point. Nevertheless, what happens if we assume that all particles classical and quantum have a size? Let us assume that each particle with mass can interact gravitationally with itself because each particle with mass, classical and quantum, has a size. Then, discounted the energy associated with the mass, the total energy of an isolated particle is the sum of its kinetic and gravitational energies. As discussed in shorts number 2 and 4, the potential energy associated with a self-attractive interaction, electrostatic or gravitational, is negative. Its absolute value increases if the size of the particle decreases. However, as discussed in short number 2, if the quantum particle is in the wave where its energy is dA plus mc2, then its kinetic energy is positive. Moreover, its kinetic energy increases when its size decreases. The opposite behavior of the kinetic and potential energies determines the possible existence of a size of the particle where its total energy is minimum. This would be the size of the quantum particle. We can estimate the kinetic energy of a spatially confined quantum particle as we discussed in short number 2. We can use the results obtained by solving the PPGP equation for a one-dimensional infinite well. This was discussed in short number 1. The kinetic energy of a spatially confined quantum particle is positive if the particle is in the wave where it has an energy equal to dA plus mc2. Moreover, the kinetic energy increases if the confinement of the particle increases. Using this result, we can obtain that if the mass of the particle is smaller than the Planck mass, then the wave associated to the particle has a non-null size. The Planck mass is approximately equal to 22 micrograms. This means that if the mass of the quantum particle is smaller than 22 micrograms, then there is a wave associated to the quantum particle. The quantum particle is then a quantum particle. However, if the mass of a quantum particle is larger than the Planck mass, the wave associated to the particle collapses to a point. quantum particle gets naked, therefore, it behaves like a classical particle. This is the reason nobody has ever seen the Schrödinger cat. Cats have a mass much larger than 22 micrograms, therefore, all cats are classical particles. There is no wave associated with any cat. However, atoms and molecules have a mass much smaller than the Planck mass, therefore, they are quantum particles. All these mean the existence of numerous classical objects around us constitutes an overwhelming amount of evidence about the validity of the Einstein special theory of relativity. Details about this topic can be found in a recently published book titled Relativistic and Non-Relativistic Quantum Mechanics, both at once. This book was published in September 2023 by Springer Nature, in the undergraduate lecture notes in Physics book series. The book was written by Professor Luis Grave de Peralta and his collaborators from the Department of Physics and Astronomy at Texas Tech University, Lubbock, Texas, USA. This book is based on the use of the Poveda-Poey-Grave de Peralta, PPGP, equations. In addition, the authors used the PPGP equations for illuminating discussions about the following topics: the frontiers between the classical and quantum worlds, how the interplay between quantum mechanics and relativity determines the existence of black holes, the observed asymmetry between matter and antimatter. A Spanish translation of this book is also available in Bookhaven.